We're now going to see how power series can be used to find solutions of differential equations. So here we have two of our power series expansions, so our Maclaurin series and our Taylor series. Remember that what we've got here is function notation, so we have f prime of x, which obviously means differentiate with respect to x. Now if I want to find f prime evaluated at 0, another way I can write that is that I've got dy by dx evaluated at the point where x is 0, or perhaps so that we can write slightly quicker, I'm just going to write evaluated at 0. Armed with this knowledge, we can now get straight into questions. So here we want to find, using a Taylor method, the series expansion in ascending powers of x, up to and including x cubed, of the following differential equation, given the following boundary conditions. Now I'm told here that my boundary condition is that x is 0, so I'm going to evaluate all of my functions at 0. I know that y evaluated at 0, given to me here, is 1. I want to find dy by dx, evaluated at 0, which again comes from my boundary conditions and is 2. I want to find d2y by dx squared, evaluated at 0, which will come from here, y evaluated at 0 minus sine of 0, which is 1 minus 0, or 1. Next I need to find d3y by dx cubed, evaluated at 0. Well, where's this going to come from? If we go back to our differential equation and we differentiate our differential equation, we end up with d3y by dx cubed is equal to dy by dx minus cosine of x. So I can now use this and evaluate this at 0 to find out that d3y by dx cubed is equal to dy by dx evaluated at 0 minus cosine of 0, which is going to give me 2 minus 1, which is 1. So I can now go from here to write my final solution, which is going to be y is equal to y0, which is 1, plus dy by dx, lots of x, plus d2y by dx squared, lots of x squared over 2 factorial, plus d3y by dx cubed, which was 1, lots of x cubed over 3 factorial. And again, just tidying up, I'm going to get 1 plus 2x plus x squared over 2 factorial plus x cubed over 3 factorial. Now this isn't my full solution, I know I'm going to have further terms, but this suffices as I only need up to including terms in x cubed. In this question I'm given a new differential equation and told that y is 1 and dy by dx is 2 at the point where x is 1. This time I want to find a series in ascending powers of x minus 1, up to and including the term in x minus 1 to the power of 4. Because I'm looking for a power series in x minus 1, I want to use this formation of the Taylor series, where my x minus 1 is going to be equal to their x minus a, which tells me that my a value is 1. So I'm going to be evaluating all of my functions at 1. So let's start with that. I know that y evaluated at 1 is given to me here because I know that when x is 1, y is 1. I know that dy by dx evaluated at 1 is also given to me in the question. d2y by dx squared evaluated at 1. Well, that requires me just to rearrange the equation that I've got here. So dy by dx, d2y by dx is going to be equal to x times y, which is 1 times 1, take away 2 lots of dy by dx, so take away 2 lots of 2, which is going to give me minus 3. The next term I need is d3y by dx cubed evaluated at 1. Now, similar to our previous question, what I need to do at this point is to differentiate the function that I was given originally. Okay, if I straight out differentiate that, I'm going to end up with d3y by dx cubed plus 2 lots of d2y by dx squared. That's my left hand side. For my right hand side I need my product rule because I'm multiplying two functions together, and I'm going to differentiate that implicitly. Differentiate the x and leave the y. Leave the x and differentiate the y. And I end up with this. Now, evaluating that at 1 would be equivalent to, well, if I subtract my two lots of d2y by dx squared, it's going to be the same as y evaluated at 1 plus x times by dy by dx evaluated at 1 minus two lots of d2y by dx squared evaluated at 1. Looking back through my working, this is 1 when x is 1, dy by dx was 2, and this was, from my previous part, minus 3. Putting all of this together, that's 1 plus 2 plus 6, which gives me 8. Or rather, if I stop and check again, this is 1 plus 2 plus 6, and silly Mr. Pett, it should be 9. Now, as I run out of room on my page, the next thing that I want to find is d4y by dx to the power of 4, evaluated at 1. I know I need this because I'm looking for terms up to and including x minus 1 all to the power of 4. This now means I'm going to have to differentiate the function that I've just differentiated. Again, this is now going to give me d4y by dx to the power of 4 plus two lots of d3y by dx cubed, which will be equal to dy by dx, and finally product rule on this will give me dy by dx plus x lots of d2y by dx squared. Given the mistake that I've just made previously, I want to calm myself down and make sure I do this properly. So, substituting in the value 1 is going to give me, well, this will give me two lots of dy by dx, evaluated at 1, that was 2, so this gives me two lots of 2, x lots of d2y by dx squared. So here's my d2y by dx squared, my x value is 1, so I want to add on 1 times by minus 3. And finally I need to subtract two lots of d3y by dx cubed. So I need to subtract two lots of my previous answer, which I've now corrected, to give me 9. Slowly does it to give me 4 minus 3 minus 18. 4 minus 3 is 1, 1 minus 18 gives me minus 17. Okay, now it's time for a quick clear up of my board. That's better. I'm now ready to attempt my final solution. So, reading straight from my Taylor series, I have y is equal to f of a, well that's going to be my y evaluated at 1, plus, for me, I've got x minus 1 times by f prime, well that's going to be dy by dx evaluated at 1, plus, and then continuing, x minus 1 squared over 2 factorial, the second differential turned out to be minus 3, plus x minus 1 cubed over 3 factorial, the third differential turned out to be 9, and finally x minus 1 to the power of 4 over 4 factorial, and the differential turned out to be minus 17. Now let's get to a point where we can tidy that up. 1 plus 2 lots of x minus 1 minus 3 over 2 lots of x minus 1 squared. Now I'm going to get some cancellation here. The 3 will cancel with one of my 3's in 9, which gives me 3 over 2 lots of x minus 1 cubed. And there's no getting away from this one. That's going to be 17 over 24 lots of x minus 1 to the power of 4. And so it would continue. Here's my final solution. Okay, thanks for watching. Sorry for the mistake. Good job we caught it in time. Just time for you to practice now. Don't forget to check out the website.